Okay, let's work on finding the area between two curves. So remember, we know how to find the area under a curve, and that's just the integral of f of x from a to b. And so what we want to do is work on the area between two curves. And so if you imagine that you have some function f of x, the area underneath the curve would be all of this pink area. Let's imagine we're going from A to B. And then if you draw some other function, g of x, what we're trying to find is the area between those two curves. So this area in here. Well, remember we had that pink area that was all underneath. If I did a similar thing with the blue area, I could draw it underneath as well. And to find the area between the two curves, I would just subtract. So what I do is f of x minus g of x. Notice in this example that f of x is bigger than g of x for all the x in my interval. So f of x you can think of as your top function, okay? And g of x is your bottom function. What you're going to see in some of these examples is if the top and bottom change, then you're going to have to maybe do different parts. Okay, so the first example says find the area bounded by the curves of y equals x squared plus 2, that's this one, y equals negative x, that's this one, from x equals 0 here to x equals 1 here. And so what we're looking for is this area here in those curves. So if we use the formula from the top, we say we want the integral from 0 to 1 because that's where my x starts and ends. My top function, f of x, is x squared plus 2 minus my bottom function, g of x, is negative x dx. Before I find the integral, I'm going to do a little bit of simplifying. X squared minus negative x makes plus x plus 2 dx. This is a definite integral, so I'm going to integrate, add 1 to the power, divide by the new power, add 1 to the power, divide by the new power. And then I'm going to use the fundamental theorem of calculus. Remember that says plug in 1, plug in 0, and see what you get. So 1 cubed over 3 plus 1 squared over 2 plus 2 times 1 minus 0 gives me 17 over 6. So the area in here is 17 over 6. Okay, let's try another example. And again, it's helpful to you if you draw the sketch yourself. So find the area bounded by the curve y equals 2 minus x squared and y equals x. So over here, I'm going to draw those curves. I know that 2 minus x squared looks like this. If you don't know that, you put that in your graphing calculator, okay? And I know that x looks like this, x. And what I need to find is the area between them. So I'm looking for this bounded region, the area of that bounded region. To do that, I need to know these intersection points, okay? Because I need to know what a and b are when I set up my integral. To find those intersection points, I'm going to set these two functions equal to each other, and I'm going to solve. You can solve this using your calculator. You could solve this by setting it equal to 0 and factoring. However you want to solve. But I get negative 2 and 1. So this intersection is at x equals negative 2. This intersection is at x equals 1. From there, I can set up my integral, negative 2 to 1. Remember, I do the top function, which in my picture is 2 minus x squared, minus the bottom function, x dx. Again, I'm going to integrate. So I have 2x minus x cubed over 3 minus x squared over 2. I'm going from negative 2 to 1. I'm going to plug in my numbers. So 2 times 1 minus 1 cubed over 3 minus 1 squared over 2 minus 2 times negative 2 minus negative 2 cubed over 3 minus negative 2 squared over 2. And I compute that value and I get 9/2 or 4.5 for my area. Again, if you remember how to do definite integrals in the calculator, you could take this definite integral back here and put that in your calculator and it will give you the answer of 9/2. So if you remember how to do that, you can do that as well. Okay, another example says, set up the integral that allows you to find the area in the first quadrant. So if I'm shading in the area I want here in this picture, I just want that area right there. And what I want you to notice about this is that before 6, the bottom of this function looks different than after 6. So this has two parts. It has this part here before 6, where the bottom is the x-axis. And then it has this part after 6, where the bottom is that line. Okay, so you want to make sure that you're going to set this up, this integral up, in two different parts. One part is going to go from 0 to 6, and the other part is going to go from 6 to this intersection, 9. Okay, so you're going to set this up in two different parts. One part from 0 to 6, and the other from 6 to 9. Okay, this top function is square root of x, this bottom function is x minus 6. So in the first one, I'm going to do top square root of x minus the x-axis, which is 0. And in the second one, I'm going to do top square root of x minus bottom x minus 6. Okay, so this is the green area. And the other one is the pink area. Okay, so we set that up as two different integrals. And then you evaluate. And again, you can do this. Oh, we just have to set it up. You don't even have to evaluate, just set up. You can be done there. Great. Okay, so I had to set it up as two integrals and add them up. If we couldn't see that this intersection was at 9, we would set these two equal and solve. Okay. Okay, let's do it again. So this one says, set up the integrals to find the area bounded by those two curves. Okay, so what I would do is I would go to my calculator and I would draw these two curves. And when I draw these two curves, I get something that looks like this, which is the 3x cubed one. And then something else that looks like this, which is the negative x squared plus 2x. I did a bad job here. This should go down like that and cross right there at the x-axis. Okay, so what you want to notice is that these have three intersection points. And again, I have this piece here where the x cubed piece is on the top. And I have this piece here where the x squared piece is on the top. So when I set this up, I'm going to have two integrals. And I'm going to add them up again. And I have this pink one where the x cubed is on the top. And this green one where the x squared is on the top. So the only thing I'm missing is those bounds. And to find those bounds, I need to find these three intersection points. This one looks like it's at 0, okay? So again, you can find these intersection points however you want. I'm going to use the calculator to find these intersection points, okay? And when I do that in the calculator, this one is at 2, and this one is at x equals negative 2. You can also set these two equations equal to one another and solve, whatever your favorite method is, okay? So when I'm writing this first integral, the pink integral, it starts at x equals negative 2, and it stops at 0. Remember, the x cubed function was on the top, minus the x squared function on the bottom. And then this second integral, the green one, starts at 0 and ends at 2. The squared function is on the top, and the cube function is on the bottom. Let's make these black so you know those are the answers. Okay, one more example. Set up the integral to find the area bounded by these functions. What I want you to notice about these functions this time is that they're kind of curving in the other direction. And if you look at the equations, they say x equals instead of y equals like our other pieces did, right? So if you're thinking about this, what I want you to think about is making a horizontal rectangle. Remember when we found areas to start in the last piece? We talked about adding up the sum of a bunch of tiny rectangles. In this case, I want your rectangles to go horizontally. Okay, and so what we say here is that we integrate with respect to y. So my variable this time is going to be a y. And so when I do things with respect to y, I'm going to do right minus left. And these bounds are going to be y values, okay? So I need this y value down here, and I need this y value up here, okay? This y value looks to be at -2, so that's going to be my bottom bound. This y value looks to be at 1, that's my top bound. My right function, this one, is the curvy one, x equals 3 minus y squared. And my left function, that line, is x equals y plus 1. So I'm going to do right, 3 minus y squared, minus left, y plus 1. And then I can integrate this, okay? I don't have to, though. I just had to set it up. But notice this time my variable was with respect to y, and my bounds were y values. And when I do y's, I'm always going to do right minus left, because on the right, things are bigger than they are on the left.